In this video, I would like to illustrate how the basic comparison test can fail, which means that we'll need to use different tests, and that's going to be the limit comparison test. So let's use this example. We need to determine whether this series converges or diverges. So we have series as n goes from 1 to infinity of 2 over square root of n plus 2. So if I attempt the comparison test, then the obvious series that I can use to compare my series to is going to be the p series. Here's its general term. So first I'm going to write down the general term of my series, and then I will compare it to this following general term, 2 over square root of n. Well, I can see that this denominator is larger, which means that the overall fraction is smaller, right? So I'll use less sign. And this is the general term of this p series. 2 over square root of n, well, it's same as 2 over n to the power 1/2. Right, so that's p series. Power equals 1/2, which is less than or equal to 1. Therefore, this series diverges. But now, knowing that this larger series that has larger terms, diverges, can I say anything about my series that has smaller terms? Well, since the series diverges, it means that its sum is infinity, right? Well, when I add up larger terms and I get infinity, can I say what happens when I add up smaller terms? Actually, no. Well, as I add up smaller terms, I can get infinity or I can get a finite sum. This means that we're looking at the case when the comparison test fails. Well, we'll have to use different tests, and that test will be the limit comparison test. Their names are similar, but, well, the second one is called limit comparison test, so that means that we're going to set up a limit. And this is how the limit is set up. We're going to take general term of our series, let's call it a sub n, so that is a sub n. And we're going to take the general term of the series that we know either diverges or converges. Well, we're still going to work with this p series. Let's still use it. We know that this series diverges, right? Well, its general term is b sub n. So we're going to set up the limit of the quotient a sub n over b sub n. So limit as n approaches infinity of a sub n over b sub n. So that means that it's going to be, as n approaches infinity, a sub n, 2 over square root of n plus 2 over, and then b sub n, 2 over square root of n. Well, this is a complex fraction. To simplify it, I have to take the numerator fraction and multiply it by the reciprocal of the denominator fraction times square root of n over 2. As we can see, 2's will divide out, and we get limit square root of n over square root of n plus 2 as n approaches infinity. And now what we have here, we have an expression with the same degree in the numerator as in the denominator. And that's the case where we can use a shortcut, and the limit will be equal to the quotient of the leading coefficients. So the coefficient of the numerator is 1. The leading coefficient of the denominator is also 1. So it's 1 over 1 equals 1. And according to the limit comparison test, if this limit equals a finite positive number, so that means that it's greater than 0, then either both series converge or both of them diverge. So we know that the series where we got the b sub n term diverges. Well, that means that our series, the one that has a sub n term, also diverges. So here's the result. Series diverges by the limit comparison test.